Okay, share screen. Okay, great. So, welcome to our large language model class. And our main source for this class will be this GitHub, where you will find the information for each week. And so for week 1, I have uploaded some materials. So I don't know, did you see the syllabus? If not, I can put up. So syllabus is on my courses. So we will have 10 homework assignments, but beginning from homework 7, the topics will be more complicated, like retrieval augmented generation, quantization, or reinforcement comment. So beginning from homework 7, you can choose one of the homeworks as your final project, because the homeworks will be very large. So in this case, you don't need to do this homework. You can transform your homework in your final project. And so that's why there is 11 minus 1. So you can do 10 homeworks and 1 project, and then the related homework to your project will be counted. And yeah, we don't have other assignments. Also, my plan is, because you're kind of some of your 5th-year students, to hold our class also on Zoom. So you don't need to attend the class. If you want, you can just join from home, or where we are, or watch just later the recorded videos. So this is my plan, to make you, because it's maybe hard to come 3 times a week on campus. So feel free to also join on Zoom. It's important that you just understand the material and are able to solve the problems. So these are topics. Before until the end of this month, we won't need GPUs, and I filed the request for computational powers, but they will consider this. They will provide the answer in month. So, but we don't need this for the first month. If they won't provide our access to GPUs, we will use Colab or some other resources, just pay $10 for a month. And but hopefully they will provide. It's a specific NSF program for classes. Yeah, so the central part will be, I believe, transformers of our class, because all the models are based on transformers. And the second part will be applications of large language models and fine-tuning. And also, I a little bit changed this original syllabus I added the multimodal large language models as the last topic, like models that work with images and text, not just with text. Okay, so the other source for our class is sorry. Oh, I include this in week one. Is this NLP course for you? This course was created 9 years ago, but it was updated with each year. So the last topic here is transformers, I believe. But it's a nice source for interactive practice. So for example, for today's topic, we will talk about word embeddings. And here you will find, for example, visualization, also a lot of links to papers and, for example, visualization of word embeddings. But we'll go back to this in the end of the class. And also, I'm using these, at least for the first weeks, because it's general NLP topics, the slides created by the author of this course page, Lena Vojta. So, okay, let's get started. Yeah, and this is the first time we teach this class in our department, so there might be some unexpected problems during class, but I hope it will go smooth. Yeah, so these are the requisites of the course slides that I'm using for today. So the plan for this week is to understand how to represent texts or words in computers. So we will talk about vector representation for words. And today we'll stop on word to vec, because those lectures were developed for 3 hours class, but we have 3 classes by 15 minutes. So, okay. So why do we need word representation? I kind of answered this question because we should represent somehow texts in computers, and they are represented only digitally. 1 second, I will move this. Yeah, because computers don't understand sentences like I saw cat. We should represent every token with a vector. And then we can use these vectors as input to our algorithms. So the simple idea is to create a dictionary and just number every word in our language, and create a dictionary that maps every word to a digit. And then we create this lookup table where index is the index of the word in our language. And this is a one-to-one mapping. So every word will be mapped into a digit. So different words have different indices. And what if some words are missing in our table? For example, misspelled. Then these lookup tables contain unknown token. Typically, it has index 2 historically. So after we created this lookup table, we can use the very simple approach to create one-hot encoders. So I want to ask, guys, did everybody take the machine learning class and knows what is this one-hot encoding? Okay, so after mapping every token to a digit, we can create vectors of the size of our dictionary with 1 on the position of our word index. So what are the problems with this representation? Now I want to ask you. So we created actually the vector representation for words, but what, yeah.
Couldn't your vector get way too big if your dictionary becomes too large?
Yeah, this is one of the main problems, that the number of words may be 300,000.
There's a lot of wasted information.
Yes, efficiency, it's related to this sparse representation. More problems? So do you remember how we calculate the distance between vectors, like L2 distance? So we have the distance between, for example, one word and the other words. What will be the distance between two one-hot encoder vectors? So the square root of 2, because we will have 0 minus 0 squared plus somewhere 0 minus 1 squared and somewhere 1 minus 0 squared. And the sum will be always 2. So all the words will be equal distant, but maybe it's not very realistic, because some words are grouped together, some words so another problem that we don't take into account we assume that all the words are orthogonal. Some other problems. What follows from this equal distance?
Does it mean you have no notion of similarity?
Yes, and similarity relates to some meaning of the words. So this representation doesn't reflect any higher level information about the words. So what is the meaning of the words? So this is actually, this question doesn't have an answer because sometimes we can't explain ourselves even on our human language. And the same word can have different meanings for different people. But still, let's think about what is the meaning of the word. So, for example, I hope you don't know the meaning of this word тезгуина. But let's try to look at the sentences with this word. A bottle of this word is on the table. Everyone likes this word. This word makes you drunk. And we make this out of corn. So can you have any idea now what does this word mean? Yes.
It's like vodka or liquor.
Something alcoholic drink. Yes. So let's think about how you came up with this idea. So what helps you to understand the meaning of this word? Of course, it's not like definition of the word because it's still with just guessing, but yes.
Context is used then?
The context. What is the context?
It's for a bottle making drunk.
Yes. Like, because we know that some, I don't know, whiskey makes you drunk. So I saw some other ideas. Yes.
Where is the position of the word in the line?
Position, well, for English language, the word order is important. For some languages, you can replace the... So what is the context? So you said that the context actually helped. Yep.
Is it associating with other words that you're using? And for example, you're associating with like drunk or
Yes.
Bottle.
Yes, because you saw some words in this context, different words in this context. And now you can associate like your previous knowledge with this unknown word. So in natural language processing, by context, we mean the neighboring words. It can be the entire document, like this word in the document, like in Wikipedia, or typically we look at some window, like 5 words from the left and 5 words from the right. Yes, here is example how we can explain like our real life understanding of meaning in numbers. Like if we try the word motor oil, it can be on the table, motor oil, so it satisfies the first context. But maybe it doesn't satisfy the second. Not everybody likes motor oil. So we look at like you can look at all the words in your language and try to put these words in the place of our unknown word. And then you will have like these matches. And in this example, wine has more matches. So we can say that this тезгуин is kind of alcoholic drink. It's called a distributional hypothesis. First, it was introduced in 1954, but typically articles cite the later paper. But it was introduced in 1954 by Harris, and this hypothesis says that if we see very frequently two words in the same context, then these words are similar. Now, we will use this hypothesis in practice when we convert our words into vectors. And then you will see all these like two paths. You can use count-based methods or neural network or model-based methods. And count-based methods are explainable because we will just count, for example, frequencies of words. But as you know now, everybody uses neural networks. So, but they're less explainable. So maybe if you want explainability for your project, you may use still count-based methods. But I think in 1-2 years, maybe everybody will use neural network methods. So how to represent better words with count-based methods and neural network methods? The main idea for count-based methods is just to count words. For example, if you have the document, you can just count how many, for example, word cat was mentioned in this document, maybe 0. And this is the idea. You can create this table with words from your dictionary in rows and from the words in your dictionary in columns. And then you create, for example, so for example, this is the word in rows, the central word. And then you look at, in my case, 4 neighbors of this word. So these words will be context words. They will be in columns. So this is the central word. And these words we call context words. And you can count how many times, for example, so you just go run window through your document, and you will just count how many times the central word had a neighbor in this window size, like in my case, 4 neighbors with another word. So you will create this matrix. Do you understand how to create the matrix? So it's you just count the frequencies of your context word in the window around the central word. And then you can apply SVD decomposition. So typically we use U sigma V, but in slides they use V sigma U, but typically we use U sigma V. And every matrix can be decomposed as U sigma V, where sigma is a diagonal matrix. For example, matrix n times m, where u will be n by n and v will be m by m. And sigma will be a diagonal matrix with positive numbers on the diagonal. And U will be a matrix of eigenvectors of matrix A times A transposed. And V will be the matrix of eigenvectors of A transposed A. So after this decomposition, we can take, because it's the matrix of positive numbers, we can take square root and decompose as U again. They use V, but typically U is the first derivative. You work with SVD.
You do U, sigma, U.
Yeah, usually U, yeah, they use, yeah. So we can use the square root of sigma. And then this matrix will be the matrix that represents the central words. And this matrix will be the matrix that represents the context words. And we will get actually a matrix decomposition. And so this is one way to create word embeddings better than one-hot encodings. What is, yep.
Are both the sigmas supposed to be square rooted?
Yeah, oh, sorry. You're right. Of course. Because the product should be just sigma. What is the problem with this approach? Yes?
It's time consuming to calculate.
Yeah, for example, this is one problem. But what if we want to create word embeddings based on a huge amount of texts, like now large language models are trained on like Wikipedia is just 1% of this data. So what will be the problem with this huge amount vocabulary? The size of the matrix. So it's just impossible to try to perform SVD decomposition on matrices larger than 1,000, for example, and the number of rows is hundreds of thousands. But this is the idea. For example, cat is the central word, and in gray, the words that we call context words. So every word will have two representations. And this idea is important because it will be used also in transformers. So every word will get two representations. One representation in the left matrix and another representation in the right matrix. So in the left representation, this word will have embedding as a central word. In the next matrix, it will have embedding as the context word. So I mentioned in my ML class, it's kind of when I teach at RIT, I'm in one role. When I'm going to UFR, where I'm a PhD student, I'm in another role. So the same is here. Every word will have two roles. And so then we can create a matrix. I explained how we can create this matrix with counts of the words and contexts in some sliding window of this word. A little bit improvement of this matrix is to calculate mutual information instead of just counts. It will take into account very frequently used words. And this idea is called PMI, positive mutual information, because we kind of clip from below. Another idea is to use document classification. Then you can count how many times one word was mentioned in the entire document. And based on the counts of the words in each document, you can say that documents are close, because again, we assume that similar documents contain similar words. So it's another way to build this matrix. Then when we perform this decomposition, the second matrix will represent actually the embeddings of the entire documents. Now let's move to the, well, this modification TF-IDF. We will skip it. We will skip to model-based embeddings. And the first model was introduced in 2014, was words to vec. So the main idea. We will create the again for each vector, we will create embedding. So, for example, okay, this is the idea. So again, for each word, we will create two vectors. How to find these vectors, we will talk a little bit later. For now, we assume that we have some vector representations, two vector representations for each word. And again, we use the sliding window with the central word as the central word and neighbors as the context words. And then we want to use maximum likelihood estimate. And maximum likelihood estimate is just the maximization of the probabilities. Again, in a few slides, we'll talk how to actually represent these probabilities. And we calculate the probability of each word in context to be in this sliding window with our central word. So this is the conditional probability. What is the probability to meet, for example, word cute with A? Probability to meet gray in the sliding window that contains A, and so on. And then we go through the entire corpus of our texts. And now I will explain how we calculate these probabilities. Then we calculate these probabilities, but conditioned on the next central word, and so on. So in your in code, you will just create pairs, a central word and context word. Or maybe the first will be context and the second will be central. But for the entire document, you will create these pairs, like soul and cute, gray and cute, cat and cute. Then you move to gray. You will create new pairs. You will a gray, and so on. So this will be your actual training set. The pairs of words where the first or the second is the central word, and the other is the context word. After that, we should define the loss function. And the loss function will be the product of probabilities. So we go through all the words. So T corresponds to the central word. And the second product goes through the neighbors of our words with index T. And M is the size of our sliding window. And now we want to define actually what is the model, what are the parameters that we want to maximize. That want to define, that will maximize the likelihood. But actually we will minimize the loss function as the negative of likelihood. We will minimize the negative function. And also we add this division by the number of points, but we will use stochastic gradient descent. And in stochastic gradient descent, we will use just 1 point at a time. So we will work only with the second sum over the neighbors. Okay, now how to calculate these probabilities finally. So we we have 2 vectors for one word. For W, we have 2 vectors. One is context, one is central word. And here is the word cat plays the role of the central word. Here, the word cat plays the role of the context word. And if you remember ideas of recommendation systems, we can take the dot product between 2 embeddings and get some score. So here is the same idea, to take the product between the central word and representation of the context word, just dot product. And to get the probability, we apply softmax. And softmax will normalize this numerator by the sum over all words in our dictionary, so over the entire dictionary of size V. And finally, our loss function. Okay, here's the illustration that we calculate the dot product of this word with all the words, but with gray representations, and sum up these dot products. It will be denominator. At this point, it looks like by time complexity, it's no better than count-based methods. But because why this word-to-vec became very popular? Because of two optimization tricks. But before we go to these optimization tricks, I think we have some few slides about the model itself. So how this softmax actually function works? Because it will return just the numbers that sum up to 1, like P1, P2 probabilities. If our model will increase the probability that one word, central word, was more frequent in context with another word, then it will increase, for example, it will increase one probability. But if it will increase the probability for one word pair, what will be with other probabilities with other words? What?
They'll decrease a little bit.
No, the sum should be 1 always. To keep the sum the same, they will decrease. So it's kind of, if you have a pizza and if you take the larger piece, then your friends will get smaller pieces. So this is the first idea that will be useful. Yes, and it's softmax because it returns not just hard classification 0, 1, but numbers between 0, 1. I will skip this illustration. Yes, as I mentioned before, we will use the stochastic gradient descent. So this, there are slides about some math. We will skip this because we won't calculate gradients. TensorFlow or Torch will calculate gradients for us. So we don't need this. But but here's the idea. Because we use SGD, we work just with one central word instead of the sum over T words. And when we apply log, then we will get the dot product minus the log of sum of the denominator. But it's just some training details. And on every step of gradient descent, we will improve only one of these mutual probabilities of these word pairs. And here is, I will skip. And here is the idea of the optimization. It's called negative sampling. Let's see if, we have just 1 minute left. So the idea of negative sampling was, instead of using in our denominator all the words from the vocabulary, just use some k words. In this case, instead of calculating the dot products between all the words in the vocabulary, we will calculate only the dot product between some k. In practice, it's about 10 words. And it will speed up the training a lot. I will just show you the code for, and you can train this just in few hours on your machine. So here is okay. Let's stop here. I will show the code next time. I was thinking to give you as a homework, but then I decided we will have a lot of homeworks and I will just show you to understand better the model. because I typically understand better if I see the code. Okay, so yeah, that's it for today.